Hi, my name is Curtis Whitson. I'm going to talk about spatial fluid variations in tight unconventionals and related to rate transient analysis. This is a regional fluid variation map of the Eagleford. Most people are familiar with. Up in the north, you've got low GOR oils that transition into dry gas in the south, and all fluid types in between, from basically volatile oils, near critical fluid systems, gas condensates, and down to dry gas. This is also for the Barnett, which is considered normally a dry gas field, but you actually see up in the northern part that you actually have local variations. And you have an oil region with GORs from 500 cubic feet per barrel to 1,000 to 2,000, and quite a small range, large range of GORs over smaller areas. So what we're talking about is basically the GOR variations within a well box. First, we're going to talk about the GOR, producing GOR of a single layer, and in particular during infinite acting flowing period. It's the function of flowing bottom hole pressure, which can vary with time, the in situ solution gas oil ratio, and the degree of undersaturation. We'll also talk about the spatial distribution of in situ composition or solution GOR. Basically, it's expected to be found in some variation in all directions, but with the most important being that in the vertical direction. And layer-wise, according to paleo sequences, and this layer-wise GOR variation also poses a problem of uniqueness and history matching, because we don't often have data that give indications of what those GOR variations might be, unless, of course, you use mud gas indicators, which I'll talk about in a little bit. We do show in a couple of papers that the variation of in situ GOR in the lateral direction is not really important to getting the producing wells GOR variation locked in, and show some examples of that as well. And then finally, as a summary, the multi-layer producing GOR variation with time is a function, of course, of the individual single layer producing GORs with time, but basically how the layer contribution from each of these layers changes with time, which is a function of how the layers deplete differentially according to KH and the volume in place of each layer, and the layer PVT properties, particularly viscosity and also compressibility. These are the papers that are forming the basis for the presentation today. So if we look at the fundamental single layer 1D linear flow behavior of a uniform composition, and in particular during the infinite acting period, we showed in the 2012 paper that the producing gas oil ratio is expected to be completely constant throughout the infinite acting period if a flowing bottom hole pressure, constant bottom hole flowing pressure is maintained. This was proved semi-analytically by a couple of authors later, and also by Steve Jones in numerical simulations of oil systems. These simulations are typically that of a planar fracture, symmetry element in a well. We do simulations of the entire well with all of the fractures when we look at heterogeneous properties, GOR and petrophysical properties, and in some cases we use the symmetry element model. This is an example of a near critical oil, 4,000 GOR solution, OGR of 250 barrels per million. Basically gas rate in red, oil rate in green. We've got both compositional black oil runs here. The log-log plot with linear half slope here basically is showing infinite acting behavior. Bottom hole pressure is 1,000 psi. What we want to look at is the ratio of oil to gas rate. You can see that it's completely constant throughout the entire infinite acting time of 1,000 days here at about 20 barrels per million. We introduced in that paper a dimensionless infinite acting producing oil gas ratio that reflects basically how the oil rate will decline from the initial value when you're producing the initial solution oil gas ratio due to two-phase flow effects near the well. This is basically a map for a given fluid type, the Eagleford, at a given flowing bottom hole pressure for varying degrees of undersaturation shown here. The saturated, if the reservoir pressure is equal to this bubble point of the oil system, then basically you're along the red line here. The example we just looked at had a producing oil gas ratio of 20 barrels per million divided by the initial of 250 gives 0.075. So you can see that this was the system basically on this line here that was just off, just slightly undersaturated. So basically the GOR variation with time that is seen in basically all of these tight unconventional wells is mainly coming from the fact that the bottom flowing pressure is changing with time. And this was shown in that paper as an example where we're producing at a constant gas rate. So the flowing bottom hole pressure is dropping. It reaches the bubble point here. The gas oil ratio goes from 4,000. It decreases a little bit since we're talking in terms of oil gas ratio, producing oil gas ratio. That goes up a little bit due to the critical gas saturation, but then it quickly turns and starts decreasing precipitously down to a very low value as the bottom hole flowing pressure drops towards low value. So this is where we're getting this very large variation in producing gas oil ratio due to the flowing bottom hole pressure. Now on top of that, you can have many different changes in the well control during the life of a well, and this can cause significant hysteresis and vastly changing produced well stream properties. Not just the gas oil ratio, but the saturation pressure of the well stream, the type being bubble point or dew point, and the API gravity of the stock tank oil. This is an example again shown from that 2012 paper. It's the same exact case that we ran here, except we stopped at 30 days, the million per day, and went to 200,000 cubic feet per day to the end of the first year, at which time we opened the well up, put it on a constant bottom hole flowing pressure of 1,000 psi, and the well opened up and came with a very sharp decreasing rate for the next 2 years. And in that period, we also had a 30-day shut-in. So what we're going to look at here is how the well stream saturation pressure changes. The type changes from bubble point to dew point here. And then as we basically lower the rate, you get a change in the dew point variation. It turns back into oil when you're getting these higher oil gas ratios here. But then it turns back into a dew point system. And then when we put the well open, it turns into a dew point system the remainder of its life, including after the 1 month shut-in. So you see you get a very complex behavior of producing oil gas ratios just because of the flowing bottom hole pressure changes. The second important observation we want to talk about today is this layer-wise variation of in situ solution GOR, which is likely to be found within a well box volume, and it does matter on production performance of the gas oil ratio for a well. Now, we studied the literature of geochemical outcrop studies and core analysis and the correlation of TOC to the in situ GOR, and basically proposed that we look at a layer-wise variation of solution in situ gas oil ratio within the well box, having dimensions such as this. This is from logs over a 6 meter section. Basically here, the TOC is varying in order of magnitude. And here we have an outcrop where the TOC is varying by about a factor of 3. There's also some indication that there's lateral variation of in situ GOR along the well lateral itself, based on work by Tao Yang on using mud gas analysis. And what we show in some of the papers is that such lateral variations don't really have an impact on the overall producing well GOR, which I'll discuss a bit later. This is an example from an Eagleford well, basically along the 1 mile lateral. We've got a minimum 50 barrel per million, a maximum 150 barrel per million CGR indicator based on the mud gas data here and correlations between the two. This is basically translating into a 6,000 to 20,000 GOR variation along the lateral. So one of the things that we observed was that lateral either solution GOR or petrophysical heterogeneities can be ignored in a single value arithmetic value, or homogeneous, so to speak, porosity permeability can be used and get basically the same performance as if you map out the entire well with all the hydraulic fractures and essentially look at the producing GOR performance of that fully heterogeneous model. If that's the case, which we'll show many examples where it is, and the entire horizontal well can then be modeled accurately with a single hydraulic fracture symmetry element using the average petrophysical properties, thereby reducing the simulation runtime significantly. So basically, the GR time performance is controlled by differential contribution or depletion. And that differential depletion can actually be created solely by heterogeneity of fluid properties in the layers. That is, if the two layers have identical petrophysical properties at different GORs, they will deplete at different rates, the layers. We found that the layer with the highest in situ solution GOR will always deplete fastest, mainly because of it having a lower viscosity. At early times before the saturation pressure, the bottom of flowing pressure drops below the saturation pressure, then you can get this differential depletion only by mainly the viscosity, and that'll lead to a monotonic GOR change in the producing GOR, going from high to low, the initial to the lower, the layer with the lower solution GOR. And then finally, once you get the flowing bottom hole pressure dropping below the saturation pressure of each layer, you'll get a differential depletion. The two layers will actually become even larger. You'll have a complex. It'll be non-monotonic in most cases, and certainly a non-intuitive well-producing GOR behavior. Here are some examples from simulations that we ran. Now we're only looking at the layers having contrasting GOR, so the layer petrophysical properties are identical. But we run two cases. We run the one case with it having homogeneous constant K and phi, and the other which are based on averaging the heterogeneous map of K phi for each layer. So those are the red, and the solid black is the homogeneous approximation. This is an example, two layers, one with 1,000 and 3,000 GOR oil. Kmax came in, not too much heterogeneity, ratio of 3. And you can see that the producing GOR versus time is looking exactly the same for homogeneous and heterogeneous modeling. This is single phase flow. We're not flowing below the saturation pressure in this case. But if you were able to measure the producing GOR of each hydraulic fracture individually, you'd see that there's quite a variation from hydraulic fracture to hydraulic fracture. Take another case with the same 1,000 GOR oil and then a gas condensate with an 8,000 GOR. Basically, we see similar behavior and a wider range of the individual hydraulic fracture gas oil ratios during time. Now we're looking at a case where we go below we drop below the saturation pressure. We have a KGKO or a Kmax Kmin ratio of 4. We're again comparing the homogeneous approximation with the fully modeled heterogeneous case, again for 1,000, 3,000 in the top figure, and the next figure is 1,000, 8,000 GOR, so a gas and oil, and then the last one is 2 gas condensates. And you can see that the homogeneous approximation is very good for all of these cases. We'll look at one more with larger heterogeneities. So now we're looking at the 2 oils, 100 and 3,000. That's the same for all 3 of these cases. We're going from top to bottom. We're looking at increasing degrees of heterogeneity. What you see, though, is that this, using the homogeneous approximation, the black line, gives both quantitative and qualitative approximations of the actual heterogeneously modeled case. So in general, we can say that the producing well GOR behavior over time for any layered no cross flow system is really too complex to understand intuitively and needs to be defined by the key rock and fluid properties for all layers. And for any number of layers, not just 2, the producing well GOR is controlled by basically each layer's permeability, hydrocarbon pore volume or ultimate recovery from that layer, and the initial solution GOR. Now, what will be common for all of the layers will be the PVT model, be it a Blackwell table or an equation of state, relative permeability, mainly because we don't have different relative permeability curves for the different geologic layers, and of course the common flowing bottom hole pressure history. So this basically will define this well performance producing gas oil ratio. Here are some more examples. We're now looking at cases where the different layers have different permeabilities. This first example we have, as before, the same permeability and porosity in both layers. And we again look at this 1,000, 3,000. So we got the same behavior we saw before, basically constant GOR, and then it drops down when it gets into boundary dominated behavior. Over to the left, over to the right here, we see that the highest GOR layer depletes fastest. This green line here. And the lower GOR layer depletes slower. Down below, we can look at the contribution of the stock tank oil being produced at a given time, which is percentage is coming from the layer 1 to the layer 2, and how that changes over time. Likewise for the surface gas product. Now, if we take and make a permeability contrast so that layer 1 is now depleting more rapidly because it's got a higher permeability, but the GOR contrast is such that the layer 1 has a lower GOR, you see that this layer 1 depletes fastest, the lower GOR oil, okay, depletes fastest, but that's because of the permeability contrast. And again, the contributions of the oil and gas from the different layers is shown below. Now let's compare the two for a 10-to-1 ratio. So basically, we've got one layer with 10 times the permeability as the other. We've got the other layer with a 3-to-1 ratio or a 1-to-3 ratio. So the in-place fluids is identical for these two cases. And now we're producing, again, still single-phase flow. And you can see the dramatically different GOR profile and the differential depletion of the layers according to this exact same as just where you put the higher GOR and the lower GOR and the high and the low permeability. Now we're going to look at the case where we've got a 10-to-1 permeability ratio. We've got the 1-to-3 countering GOR ratio. And now we've got on the bottom, this is single phase as we just looked at before. And if we drop below the saturation pressure, you can see that the 3,000 GOR layer performance GOR increases like this, basically solution gas drive type behavior. The other low GOR, the 1,000 GOR layer actually has a bottom flowing pressure above the bubble point the entire time, and then the well composite GOR performance. And you can see that the difference is basically you're getting more severe differential depletion with the two-phase flow. So in summary, I'm going to show you an Eagle Ford well where we did a history match of the daily performance of a gas condensate well, initially producing around 200 barrels per million. Did a history match of a single layer homogeneous fluid, homogeneous petrophysical property. And this black line is the history match of that. What we then did is that we looked at a number of cases where we used two layers, each layer having different initial GOR, solution GOR, and each layer having different permeability and porosity averages. What we required is that the initial producing GOR was always 200 barrels per million, or 5,000 cubic feet per barrel, that they had the same, essentially the same bottom hole pressure control and the same, basically, productivity gas rate. So the gas rates matched exactly, the bottom hole flowing pressure is matched exactly. But what you see here is the difference in the producing oil gas ratio forecast for the different layered systems and the cumulative oil production. And you can't really hardly see it, but there's the black line from the single layer performance is shown down here in the bottom. So basically this summarizes the work that we've completed on this spatially distribution of fluid compositions and the effect on production performance. Thank you.